Hey, it's your guy Garrett here, and today we're going to be talking about your motherboard. Get right inside to the guts to it, find out how it works, find out its limitations, and how that affects you as a programmer. So stay tuned for that. Now, to get this party started, we need to go back to second grade math. Not because I think you're an idiot, but because some of the things that we learned back then have become just so second nature that you may have forgotten that they even exist. But they're going to help us out today. Like the fact that we use the decimal system. It's a base 10 number system. There's nothing special about it. In fact, the octal, which is base 8, or duodecimal, which is base 12, are both more efficient math systems. But we have 10 digits on our fingers, we count using digits, there was some synergy there. And back then they taught us the column system, the ones column, tens column, hundreds column, etc., where you could use the same digits, in this case 6, put them in two different columns, and they have two totally different values, like 6,000 versus 60. Now, the fact that we call it the decimal system, and I alluded to the fact earlier too, that there are other number systems out there. Back when I went to school for this, we learned basic math and conversions between decimal, which is base 10, octal, which is base 8, hexadecimal, which is base 16, and binary, which is base 2. And that base 10, 8, 16, that basically tells you how many unique characters there are in the number system. Like in decimal, we have 10 unique characters, 0 through 9. Octal has 8 unique symbols, 0 through 7. Hexadecimal is base 16, and it uses the full range of the decimal number system, 0 through 9, and to make up the other 6, they use the letters A through F. Binary is base 2 and only has 2 symbols, 0 and 1. And if you've heard anything about how computers work, you may recognize that that might just be important. Now, all of the different number systems have the same columns, like tens, hundreds, thousands, but the numbers don't have the same value. Now, like if you were counting in octal, you would go 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14, 15, 16, 17, 20, and so on. So like 100 minus 1 in our decimal system is obviously 99. In octal, 100 minus 1 is 77. In hex, it's FF, and in binary, 100 minus 1 is 11. Every number in any of the number systems can be converted to an equivalent value in any other number system. So the 87 in decimal can be converted to 127 in octal. They basically have the same value. 57 in hex, and in binary it's 1010111. And on the other side of that coin, every number system has values that, and any one of those values can be converted into its decimal value. So 100 in octal is 64 in decimal, 256 if it came from hexadecimal, and 100 in binary converts to a whopping 4. Now let's revisit that the columns. We know the columns in decimal, 1, 10, 100, 1000, etc. But how they come up with that number is because you have to use up all of the unique characters in one column before you can move to the next column. Because decimal has 10 characters, each column is going to be worth 10 times the amount of the previous column. In binary, there are only two unique digits, 0 and 1. So each column is going to be worth 2 times or twice the amount of the previous column. Other than that, they work basically the same. In decimal, you multiply the value in the column by the value of the column. So like we have 8 times 1000 plus 6 times 100 plus 4 times 10 plus 2 times 1. Add them all together and you get 8,642. In binary, it works very similarly, but you can only have values of 0 or 1. Now, anything multiplied by 0 is of course 0, and anything multiplied by 1 is that number. So it makes it a lot simpler. So you have that a 1 in the 8ths column. 1 times 8 is of course 8. 1 times 4 is 4. 0 times 2 is 0, and 1 times 1 is 1. So you have the 8 plus 4 plus 1 equals 13. Now you may ask yourself why we use such a bizarre number system for our computers, why we just don't use decimal. And the answer is here. The transistor. This is one in someone's hand, and to be honest, most of that is just packaging, just to make it big enough for us to be able to pick up and move around and put into circuit boards. In all honesty, the transistor inside, the working part, is microscopically small. There are chips, integrated circuits that you can hold in the palm of your hand that'll have literally billions of transistors on there. Now, a transistor works similar to what a faucet would do or a valve would do in plumbing. You can control the amount of, instead of water, it's electron flow through the device. And instead of using your hand to turn a knob, it uses other electronic components to control the amount of flow. And depending on the circuit, you can control how fast the transistor changes. So just like you could have a faucet where you have to make one complete revolution to go from 0 water flow to full flow, you could also have another valve where it takes 5 turns to go all the way from 0 flow to full blast. And you can configure the transistor to work exactly the same way. One thing you can also do is configure it so that it takes almost not even a turn, just a nudge, and it'll go from 0 to full blast. Nudge it back and it'll go from full blast to 0. In this case, they now call it a switching circuit because the transistor acts like a switch, just going from on to off and on again. Now, there's all sorts of data that you can store in an electronic switching device. Things like yes, no, true, false, high, low, on, off, up, down, right, left, forward, backwards, pressed or not. But probably the most powerful one is that of the binary digit, a word that was quickly abbreviated to a bit. And that, of course, is 0 or 1. Now, not very powerful in and of itself, but if you get a big group of them together, and as we said, you can get billions of transistors onto a chip nowadays, you can pretty much come up with any number that you want. Now, one downside of doing this all in a computer is that you don't get that infinite amount of virtual zeros to expand your number into. Instead, IBM on their first PC used the Intel 8088 central processing unit, CPU. That allowed data to come in 8 bits or 1 byte at a time. Now the processor itself is a 16-bit processor, but at the time there were a ton of peripheral devices that were 8 bits, and not so many that were 16 bits, and the RAM, 8-bit RAM was much cheaper than 16-bit RAM. So while the CPU is 16-bit, its data bus, the information could only go in and out of the CPU 8 bits at a time. Now when we talk about the data bus or the address bus, what we're really talking about is a bunch of little traces or etchings on the circuit board that act as wires. Each one of these lighter colored area is actually a little tiny strip of metal that acts just like a wire would, etched into the circuit board. Now both the data bus and the address bus are connected both to the CPU and to all 64K memory locations. Now if we look inside the CPU, and this is a very rough drawing of what it looks like, very basic, but there are 4 16-bit registers called AX, BX, CX, and DX, but you can at any time access just any of the 8-bit registers either as AH or AL. There's also a 16-bit register called the instruction pointer. That goes out to the address bus, and that is where you are going to point to a particular memory location. You should note also too, it's possible to move numbers from 16-bit numbers from these registers onto the instruction pointer so that that becomes the next address that's pointed to. Now if we were to zoom in on some of the RAM, it would look something like this. You notice that there are 8 bits going horizontally, and it's connected up to 1 each to a data line, D0 through D7. You note the octal comparison there. That's why it was important for us back in the day to learn octal, so you could program these numbers directly without having to use binary. But D0 hits bit 0 of every single one of the 64K memory locations, just as D4 hits bit 4 of every one of the 64K. Now the address bus, that gets a number put on there, which is basically a pattern of 1s and 0s, and this memory location here never gets activated until this pattern is on the address bus. And if this pattern's on the address bus, no other memory location can be activated. So once you put this pattern on there, which is of course, it's a number, then this is the memory location that has access to the data bus. And then there's another line, it's called the read-write line, which tells the memory location if it's going to dump its contents onto the data bus, or if it's going to read in and change its number to whatever numbers are already on the data bus. Now we still haven't seen how any of this works to make computer programs work, but this is where it all comes together. The CPU is designed so that when you first turn it on, it is going to go to memory location 0 and start executing commands from there. Now there's really 3 types of information that can be in there. There's an instruction, there's data, or an address. Now, like this first one here at I put it in memory location 0. These are kind of fake assembly language commands just for illustration. But you could have a command like move the next character into register AL. And then it puts the byte of data that it wants to move there next. You could also have the command move the next 2 bytes into register BX. And it's got the 2 bytes of data there. You can also have a command move into DX from this address, and it's got the address there. Remember I said you could move from a register to the address bus. So it can go and get whatever address you point to here and move the next 2 bytes into this register. Then there's commands like add AL into CL. Down here there's a multiply BX into DX. And then there's a jump command. And a jump command is going to actually just move the program execution from where it is now out to some other part of the code. Could be 500 bytes, 5,000 bytes away. Jump, and then you put the address in that you're going to jump to. You can also move information from a register out to some particular address. Now, this here is, like I said, kind of a pseudo assembly language, but when it gets programmed into the computer, it gets compiled into machine language, and it just looks like this. A bunch of ones and zeros. Totally unreadable by 99% of the population. So you might be wondering, how does it know which of these numbers is an actual instruction and which one is just a piece of data? And I can tell you, I'm pretty sure, so I had the book with the instructions for that 8088, and I'm pretty sure there were 74 instructions you could give it at the time. I could be wrong, it was like 30 years ago. How does it know that this one is an instruction and this one is a byte of data? Especially because you might later see that as byte of data. So it knows that 0 is going to be an instruction. This instruction inherently says it's only going to be one more byte. The CPU knows after that byte is going to be another instruction. This instruction tells it this is going to be 2 bytes of data. And then it knows there's going to be another instruction. Because it's an address, it's again going to be 2 bytes, and then there's an instruction. This one has no bytes of data, so it just knows the next one. So it just knows. It's built into the CPU based on what the instruction is. Now, this is this is assembly language. It's the closest you can get to machine language, actual ones and zeros. The programming languages that we use today are much more sophisticated, easier to type in and use. You don't even need to know anything about these registers or jumping to addresses or anything like that. It's all taken care of for you. But it's good to know this stuff in the background because it's going to help you understand some of the things that happen, why programs are written the way they are. So this was the second of the 3 foundation videos. In that third one, we're going to talk about the higher level languages that you'll most likely be using in day-to-day work. So stay tuned for that one. Thanks for watching, and if you like this, hit like and subscribe.